Hi everyone. Thanks for having me here. One of the things I was just checking is, given the amount of people we have here today, statistically speaking, probably at least two of us, actually share the same birthday date, which is, well, the birthday paradox. So let's see how this actually plays out for my presentation today. And today I'm going to be really talking about our journey to elasticity at ScyllaDB. My name is Felipe, and as I was introduced, I work as a technical director at Scylla. So if you have never heard about ScyllaDB in the past, we are basically a NoSQL distributed database designed to maximize hardware efficiency, to deliver higher throughput, lower latencies, and ultimately better TCO compared to alternatives. So at this point, you're probably thinking, well, every single database claiming the same thing, right? We are fully API compatible with Apache Cassandra and AWS DynamoDB. And the way I want you to think about Scylla is that really you can think of us like we are the most performant alternative to Apache Cassandra. And I hope I'm not offending anyone when I say this, but you can also think in the same way as, for example, Red Panda is to Apache Kafka, or Dragonfly is to Redis, in the sense that we are not only more performant solutions, but we also build upon and improve into what are some of the problems that those alternatives really have. So, of course, we do have customers. This is a list you guys can check out. And coincidentally, well, birthday paradox, I was just checking this conference website, and one of the speakers for today is actually a customer of ours, ShareChat. They are basically India's largest social media platform. And I don't know if the speaker is here, but I would like to thank you. Thank you so much for being a ScyllaDB customer, and also to invite people to really watch our talk on reducing cloud costs. Looking forward to it. So, how did ScyllaDB transition from a static to dynamic topology? It happens that when we first introduced ScyllaDB over a decade ago, we basically followed Apache Cassandra's data distribution model, heavily relying on consistent hashing, and at the time, it was really a proven way to scale persistent distributed systems. So to understand the approach we chose back then, we have to look back at its origins, right? Because basically what we did was we re-implemented the Cassandra protocol in C++. And when we think about, in general, distributing data, everything starts with a hash table, where the hash of your key points to an in-memory position which holds its corresponding value. Now, interestingly enough, if you keep everything in memory and you add an API layer on top of it, congratulations, you've just built yourself a minimalistic cache. But as it happens every single time, as you scale this thingy, you would have to eventually distribute your hash table into what's called a distributed hash table, a DHT. So you would get your hash table, and you would distribute it across multiple standalone servers. And then it would come the complexity of how do we ensure that our clients write to our distributed hashing table in a fair manner, right? And there are multiple ways we can do this. The most common way, which interestingly enough is used by, as an example, the Python main cached driver, is to basically you hash your key, and then the result of this hash, you apply the modulo operation on top of it, and you apply the modulo operation to the number of servers available in your pool. So this naive approach really results in an imbalance, which happens to reduce performance and introduce all sorts of problems, as shown here in this pie chart at the middle. Now, it happens that the Python main cached driver, as an example, is one of the most downloaded drivers. So this approach is even used today, probably by some pretty much lots of production companies scaling their main cache clusters. Now, Pinterest's Spy main cached, on the other hand, improves on that. So they do not use the model operation to distribute data, and they use what's called the highest random weight algorithm, which is basically a scoring approach that predates consistent hashing. And one of the aspects involved in this approach is that key lookups really run in linear time, right? And because ScyllaDB is a database which is built to sustain hundreds of thousands to millions of operations per second across really large distributed clusters, it happens that this scoring-based approach, this linearity, is not so good for performance. So the approach that Cassandra chose back in the days was really this notion of modern consistent hashing, where what you do is you get your servers, and you hash it multiple times across your distributed ring, which we call your key space, and with all these multiple hashes of each server you get in your cluster, this basically reduces variance and improves load balancing, with a plus of giving us logarithmic time key lookups, which is much better than linear time key lookups. So beyond key lookup efficiency and load balancing, consistent hashing actually gives to ScyllaDB and Cassandra and other databases following the same approach for distributing data another important property, which are efficient key rebalances. So it happens that in a naive distributed hash table using the model operator for distributing data, every change that you do to your topology pretty much reshuffles nearly your entire key space. And it gets actually progressively worse as the clustered scale, as you keep adding more and more nodes to your distributed system. And it happens that this is probably fine if you're running a cache, because the whole idea of running a cache is that your data is ephemeral, right? If you add a new node and you are using the model operator, probably your entire cache is going to be invalidated. You're going to see bad latency on your application, but at the end of the day, no one's going to die, hopefully. Eventually, your cache will just warm up. But since ScyllaDB is a persistent data store, all this reshuffling is simply unacceptable. So with consistent hashing by contrast, we simply remap just a small fraction of keys, and that fraction gets progressively smaller as the cluster grows. So the more nodes we add to the cluster, less data we got to string. So scaling the cluster is actually faster. Okay, so given all this quick recap on consistent hashing, we have to ask, if that approach is so good, then why did we change it then? And it happens that consistent hashing on its own has some problems, which I'm basically going to be covering in this section now. So the first problem is that if we stop and think about it, consistent hashing really follows a randomized algorithm for ownership distribution. And randomness does not guarantee perfect balance. Statistically speaking, some replicas will always end up with slightly more or less data that they own purely by chance. And this overutilization basically makes the distributed system susceptible to really load imbalances. One of the things I want you to know about ScyllaDB is that we basically follow what we call a shard per core architecture, where each CPU core in a server, in a given node of your distributed system, is observed as a shared nothing entity. So one of the things that we learned when we initially started building ScyllaDB is that those sort of imbalances could get really, really bad. So for example, if we look into the red circle here on this slide, a single CPU could get up to 6 times more traffic compared with another CPU. And this is super bad because in a distributed system, the speed of your cluster is always driven by the speed of the slowest replica. So this has a significant impact on throughput. So of course we improved on that, and we managed to reduce that imbalancing to just 20%, which is better, though it's not perfect. So on the right-hand side, I'm providing an example which I took from an Apache Cassandra blog, which exposes a similar problem. So at first glance, the highlighted node, which is kind of broken, it was supposed to highlight the node above. So one of the nodes really has 52.9% of data it owns on the ring. And at first glance, people might think, hey, this node is just handling 35% more of traffic compared to the least loaded replica, right? But in reality, once you get all those distributions and you normalize them, it turns out that this node actually handles 3 times more traffic. So this is a disaster for a distributed system, right? Even if we had perfect token collocation, consistent hashing also comes with one big assumption that actually most people don't really talk about, which is that all keys are accessed equally. And here is where the birthday paradox really plays with us. Because in reality, you know how workloads are. In reality, that's rarely true. In ScyllaDB, for example, users may create several tables, and each of those tables may have varying access patterns. Some tables can be very sparse with lots of data, with, for example, only a few keys being frequently hit. For example, imagine when you store a password reset tokens. People don't ask for their passwords to be reset every single time. While other tables can be really dense with keys spanning most of your token ring. Like, for example, if you are storing and doing things like tracking user sessions, and you have to eventually audit this data and run other sorts of operations on top of it. So those differences in users, workloads, and traffic causes discrepancies like what we observe here in the right picture. So while we have those two nodes, the yellow and the blue one, actually serving almost the same kind of traffic, we have the green one, which is actually serving much less. And it happens that if this both either of the yellow or blue nodes eventually become a bottleneck, there is little that the green node can do to actually assist. So this is a problem. Another problem, and I love the title of this slide, streaming explained them. Another problem really relates to streaming. Because when you want to scale from your distributed system, as you bootstrap a new node, what will happen is that the existing replicas in your cluster will restrict the portion of keys that they are no longer supposed to own to that node which is joining the cluster. And next, as you bootstrap additional replicas, the same keys which were initially transferred, plus a few other ones, will have to be redistributed again. So this is not just not only adds to streaming time, the time it takes for you to scale your distributed cluster, but it's also very inefficient. So at this point, you might be asking, why can't we simply bootstrap all nodes in parallel to avoid this redundant data movement I showed here? And the answer is really correctness, right? ScyllaDB and Apache Cassandra, in its original implementation, required serial topology change to ensure consistency and safety during data rebalancing. One of Cassandra's design decisions was to really use what we call the gossip protocol to propagate announcements, including topology state. And if you are not familiar with gossip, gossip is really an epidemic protocol that really can take some time to converge information, especially in larger clusters. Therefore, if we allowed parallel topology changes, we could end up in a situation where nodes could end up with conflicting views of your distributed ring. For example, one node might think that N4 has joined, while another believes both N4 and N5 are already part of the ring. And that inconsistency alone would lead to incorrect data placement and ultimately data loss, which is really terrible for a persistent database to lose data. So another thing which could happen is if two nodes are being bootstrapped in parallel and one of them fails mid-transfer, then some replicas in the cluster may have already streamed certain token ranges to the failed node, under the assumption that it would take ownership, that that operation would eventually succeed. So as a result, those ranges which are no longer owned by the original replicas at the starting state were never really streamed successfully to the node because it failed, which again would result in irrecoverable data loss. Another Apache Cassandra design decision was that they deliberately avoided relying on external coordination systems like etcd or Zookeeper in order to carry out topology changes. So in the Cassandra world and also in ScyllaDB until we implemented our changes, ensuring that you carried out topology changes correctly was pretty much a task that was deferred to administrator to handle correctly, which is pretty much a disaster. So streaming time, when you are going to scale a persistent distributed system, streaming time really depends on how much data needs to be transferred around, right? And because of our shard per core architecture, ScyllaDB was already efficient in transferring very large bandwidths of data over the wire. But as data density grew, and because clusters span multiple availability zones, we noticed that serial topology changes started taking hours, or in the worst case, it could even take days. And because of that, this basically had two consequences. First, to double the capacity of a 3-node cluster, we had to add 3 nodes of the same size. We couldn't simply add larger nodes, because smaller ones would simply receive this very same amount of traffic, and they would become a bottleneck the moment the user would start to ramp up their traffic. And because scaling took time, we also had to keep disk utilization low to stay safe, so that if we got into a given emergency room for disk utilization, we had to ensure we had enough time to scale a cluster to ensure that the workload, the user workload was never disrupted. So as a result, this basically raised costs, and the user were never able to fully maximize the storage that they were paying for. So as a result of those two consequences, most clusters were really sized for the peak, even though in reality, most users' workloads, traffic often fluctuates throughout a day. Like, for example, going from 250,000 operations per second to 1 million, as shown here in this quick chart, which I vibe coded. So just basically meant that a lot of idle capacity was simply wasted for most of the day. And this is not cool when customers start to, realizing how much money they are spending. So given all those problems with consistent hashing, we clearly have had our reasons to address these pain points, which we inherited since the early days when we decided to re-implement the Cassandra protocol. And for the rest of my talk, I am going now to explain the changes we did and how we implemented it then. So our goal was to evolve to a point where topology changes would be carried out automatically by the system in response to shifting needs. With that, what we did was we mapped a series of prerequisites we needed to build on top of ScyllaDB to really accomplish that. First one, topology changes will be concurrent with other events. Because in a distributed system, as you can imagine, there are often lots of activity that may go on. For example, users may want to restart a node while you are bootstrapping or removing another node. And we want to ensure that the system is able to achieve balance in a fair manner while taking all of these into consideration. We also wanted to our automatic topology changes to be carried out in smaller increments following sub-node granularity. So for example, instead of having to bootstrap nodes in one by one in a serial manner, we wanted it to really string data following a sub-node granularity with smaller pieces of data at a time. We also want to make the system more dynamic and all those data rebalancing more dynamic. And of course, we also wanted to finally get free of some of the consistency problems involved, which were introduced by our choice of following the Cassandra protocol. And that's exactly what we did in the first place. So what we did was, the first component we introduced to ScyllaDB was the Raft consensus protocol for managing topology changes and provide a strongly consistent view of token ownership. And it happens that Raft alone is actually part of an even larger effort in ScyllaDB to address some of the eventual consistency issues which we inherited. And Raft today provides things like strongly consistent schema changes, role-based access control, but for the purpose of my talk, Raft really manages consistent range movements and topology state. So for managing topology changes consistently, what we do in ScyllaDB is we apply a read barrier whenever a new topology change is requested. So for example, as we bootstrap the green node B, the read barrier ensures that our existing cluster participants agree on the latest topology state before we allow that operation to proceed. Otherwise, if there is a conflicting view or there is another operation ongoing, that operation really becomes serialized automatically by the system so that the administrator does not really have to worry about it. So should the user try to bootstrap or decommission another node while node B is joining, that topology change would wait until node B here streaming completed. So Raft was particularly important to effectively address the risks associated with data loss, which I explained earlier, as well as our reliance on the administrator to carry out operations correctly. Cool. So our next step was the introduction of tablets. And Tablets are really an abstraction where data on a table gets divided into smaller fragments that can be migrated as a single unit. Each of those fragments is spanning a non-overlapping and contiguous token range. So if you have a single table with several tablets, you basically the total aggregation of those tablets would span all the tokens that you would expect to observe in your token ring. Unlike Cassandra data distribution, where every table in a cluster pretty much shares the same token ring, as shown here on the left-hand side, with tablets, we are able to dynamically split and merge tablets on a per-table basis. And this means that sparse tables with very few data will have fewer tablets than denser tables. And each of those tablets can really be dynamically migrated as a single unit around the cluster as needed. In other words, the value that tablets really give to us is that we are finally able to effectively decouple topology chains from an actual streaming operation. To make this flexibility possible, we needed a way to efficiently find and update which replicas in the cluster are responsible for each tablet, as their ownership could get dynamically assigned. And rather than relying on a static mapping, like in the traditional token ring and traditional consistent hashing, we introduced what we call as a layer of indirection, which we call the tablets table. This table, which is also managed via Raft, keeps the existing mapping from tablets and which token ranges they own to its current owner replicas, allowing the system to reassign and find tablets as they get split, merged, or they eventually get migrated across the cluster. So with tablets and Rafts to manage the strongly consistency of all those data movements, we are now able to bootstrap nodes in parallel. What we do is very simple. We bootstrap several nodes, and those nodes, they will join the cluster without really owning any data. And then we have this component which I'm going to be talking about shortly. There is this load balancer, which will simply migrate distinct tablets in parallel to other nodes in the cluster until we eventually reach a perfect distribution in a much efficient manner. And the commission operation pretty much works in the reverse way. We receive the signal that two nodes want to leave the cluster, and what we do is we simply migrate their own editor tablets. We drain the tablets to other available replicas in the same availability zone in parallel. All right, so with that, we got to those smaller and the dynamic topology chains we wanted up front. We are now able to perform topology chains in parallel at subnode granularity, so we can ensure that scaling our distributed system can pretty much complete fast. But how does ScyllaDB ensure that we continue reacting to other topology chains and other events as the cluster eventually evolves? For example, how can we achieve far balance if we bootstrap larger instances, or how do we make scaling decisions based on either disk space conditions or to prevent access patterns hotspots? So the final and last component I'm going to be talking about is what we call the tablet load balancer. And the tablet load balancer decides where to migrate our tablets, which can be either within the same node to balance data across shards or CPU cores, or across different nodes to balance the load globally in the cluster. The load balancer constantly collects statistics on tablets, and it is basically configured to take several scaling decisions into consideration. For example, if one node is close to 90% disk utilization, but other replicas have 70% disk utilization, then it would evacuate some tablets from the node with highest disk pressure to the node with lowest disk pressure. If the CPU load is imbalanced, then likewise it would do the very same thing. And thanks to the load balancer, heterogeneous deployments become much more simplified. In this slide, you can see a demonstration of this on the right-hand side, where 3 nodes have twice as many shards or CPU cores than other nodes in the cluster, and our load balancer assigned twice as much the number of tablets to the larger instances to distribute traffic in a fair manner. Weighting it autonomously and ensuring that the user workload maximizes the infrastructure they are paying for without, any disproportionate balances or other inefficiencies, which are really the introduction of my talk. So this is how we got to elasticity, how we shifted from a static architecture to an elastic database solution. All these changes I mentioned are already supported in ScyllaDB xCloud, our fully managed cloud service. If you'd like to learn more, you can take some time to talk with me or my other ScyllaDB friends out of here. You can also visit our website, ScyllaDB.com. And with that, thank you so much for your time. I hope you liked it.
Thank you. Hi, this side. Hello. Hi.
Hi.
Yeah. So you mentioned that tablets, right? So
Yeah.
you can able to change the move the tablet to a different table, right? So do you have to define the tablet before actually creating the entry, or in the future, if you wanted to, maybe for example, the set of data, that this is something later figured out that you have to move it. How does it work?
So the way it works really is that the load balancer is configured to autonomously take those decisions for you. So for example, it has several inputs, as I explained it in my talk. So for example, disk utilization is one of those inputs. Key hotness is another one, so it can balance it fairly across CPU cores. When you create a table, you can specify the number of tablets you want up front. So for example, if you know that your table is going to be sparse, you probably want to start your table with a minimal amount of tablets because you want most of your data to be placed into only a few CPU cores inside your ScyllaDB distributed system. And there is another really good advantage for doing that, especially if your table is sparse, because down the road, you may want to run things like full table scans, where you want to run your entire data set, and placing all your data under a single CPU core basically makes those full table scans much more efficient. Yeah. Does that answer your question? Sorry.
Yeah, partially, but just one more thing, is there any limitation, like how big a tablet can be, how much data it can hold?
So there is no limit, but by default, a tablet in ScyllaDB it follows a logarithmic average size. So tablets are currently configured to span 5 gigabytes in size, meaning that if the data spanning that token range eventually grows to 10 gigabytes, then the load balancer will take the decision of splitting that tablets into 2. And if it grows below 2.5 gigabytes in size, then we will merge it with another tablet if there is another available. Yeah. Right? I think someone here had a question, yeah.
Sorry. Do you ever find that your load balancer causes any sort of thrashing behavior? Like maybe you're migrating some data off of a hot node to what you thought was a cold node, but it wasn't that cold.
Oh,
And both the migration and the new access patterns cause that node to be hot again. You move again, and
that's a really good question. So that's actually something we observed when we were initially implementing that. Let me give you a realistic example of what we saw in our QA. So ScyllaDB has a cache. Okay, so we implement really our own caching layer that does not rely on the operating system page cache by any chance. And what happens is that you have tablets spanning keys that are very frequently read, and you eventually decide to scale your cluster. Some of those tablets may be shifted to another node, and then those reads, which were previously hitting the system memory, the cache, are going to be go cold, right? So in order to prevent that, we do have an algorithm which we called you know how engineers are terrible for naming things, right? We call it heat-weighted load balancing, which basically means that when a query comes to the system, we will basically communicate with other replicas in the cluster so we know how hot their cache is before we allow that read operation to be routed to that particular node in the cluster. So with heat-weighted load balancing, we are able to minimize the stressing effect which you mentioned, because we always have to ensure that if the data for a particular tablet which is going to be migrated is stored in a given node's cache, we have to ensure that at least one replica still holds it after we migrated the tablet, so that we can later on slowly make that replica which is joining hotter and hotter without disrupting the user workload latencies.
does that hit weight? Is it it's propagated through Raft to keep it consistent, or do you not care about it?
No, we don't care about it because it's just reiterate information. It's propagated by gossip, really. We never got rid of gossip. Gossip is a good protocol for many things. It's not great for handling topology states, though.
All right, thank you.
No worries.
Hi, Philip. Hi.
Hi.
Thanks for the call out. So, does the elasticity here also lead to like new nodes coming up? Like, say, like clusters running on 3 nodes, and you need to scale out now. So, does it also like lead to a new node coming up, and then tablets being moved to that, or it's simply like readjusting within the existing set of nodes? And if there is a new node coming up, then there is a latency to a node getting scheduled and
Right.
and having its own spin up time, right?
Right, yeah. So if you check out the title of my talk, you will notice that I really mentioned from consistent hashing to elasticity and not consistent hashing to auto-scaling. Because auto-scaling really it depends on elasticity, but it's not something we got to yet. It's something that we are currently improving upon for a variety of reasons. We don't want to say we claim we support auto-scaling with following the same constraints as other solutions which follow auto-scaling. So the way it works today when I talk about elasticity is that whenever you can anticipate that you have a growth in traffic, you can pretty much bootstrap as many replicas as you believe you need, and then they will immediately join the cluster in parallel, and then all the load balancer will start rebalancing your data in the background for you. So you don't have to worry, you just bootstrap nodes, and then the system will manage all the rest for you autonomously. We are working on some algorithms to basically make auto-scaling possible. Currently, in our cloud, we support auto-scaling based on storage. So, for example, if you reach 90% storage utilization, that's easy. We simply go and bootstrap more nodes. But CPU-based, compute-based outscaling, this is more complicated. The way it's implemented, it's basically via feedback loop. If you think about AWS DynamoDB outscaling, this is how it works, right? There is this feedback loop which is constantly polling your workload, and as your traffic eventually grows, then it will take a scaling decision. That's how it works, and that's what we want to ensure we get right, because it has, at the end of the day, a cost implication, right? If we get this algorithm wrong, you could be paying more than you would actually want to.